All right, hello everyone. We are looking at chapter 6 now. Random variables and probability distribution. This video is section 6.1, discrete and continuous random variables. So our learning targets to start, use the probability distribution of a discrete random variable to calculate the probability of an event. Make a histogram to display the probability distribution of a discrete random variable and describe its shape. Calculate and interpret the mean expected value of a discrete random variable. Calculate and interpret the standard deviation of a discrete random variable, and then use probability distributions of a continuous random variable, the uniform and normal, to calculate the probability of an event. So, discrete random variables. A probability model describes the possible outcomes of a chance process and the likelihood of those outcomes occurring. We saw that in chapter 5 a little bit. So, here we are going to talk about, we're going to flip a coin 3 times. Our random variable is x, and that equals the number of heads obtained. So in this chapter, it's going to be super important that you clearly label what your variable is. So don't just put x equals heads, all right? It's x equals the number of heads. That distinction will make your life a lot easier in understanding what you're counting, what you're looking for, and what you're actually recording in this chance process. So x is the number of heads. So obviously you could get 0 heads. You could flip tail, tail, tail. You could flip head, tail, 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 head, tail, 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 head. You could get 2 heads, or you get all 3 heads. So the possible outcomes, this is why the number of heads obtained is super important, because it gives you the values of x right away, 0, 1, 2, and 3. From there, you can find the probabilities of each. So the probabilities of heads, remember, to find the probability of an event, is just the probability, the number of ways it can occur, divided by the total number of outcomes. So how many ways can you get 0 heads? There's only one way to do that, tail, tail, tail. There's a total of 1, 2, 3, 4, 5, 6, 7, 8 possible events out there. All right, so there's 1 out of 8. In order to get 1 head, there's 3 ways to do that, so that'd be 3 out of 8. For 2, there's 3 ways to get 2 heads, so that's 3 out of 8. And there's 1 way to get 3 heads, so 1 out of 8. So here's my probability model. Right? So a random variable takes numerical values that describes the outcome of a chance process. So the chance process is flipping a coin. This specific one is flipping a coin 3 times. And the random variable is what you're going to record or what you care about. Here, we care about the number of heads obtained. All right? You could do a different random variable for the number of tails obtained or something else, depending on the chance process. All right? The probability distribution of a random variable gives its possible values and their probabilities. All right, which is what we saw in last chapter. Now we're just doing it with a random variable, not just like a situation happening. So this is my probability distribution. All right. So the probability distribution of a discrete random variable. Remember, discrete, they have like cutoffs in it. So think back to chapter 1. Like discrete is, yeah, if you can put it on a number line and you have to make jumps. So I like to kind of remember the differences. Like shoe size is a discrete variable because it's like 8, 8.5, 9, 9.5, 10. Right? There's actual jumps. Versus the length of your foot is a continuous variable because your length can hit every number in between 2 inches to 10 inches or whatever. So that's the difference. So we're looking at discrete random variables first. So the probability distribution of a discrete random variable x lists the values and their probabilities. Remember, the other way to remember discrete is you can list all the possibilities. Like if I want to do shoe sizes, I could list every possible shoe size. I can't list every single possible number or size of your foot because it's a continuous variable. You can't list everything because you can always get a smaller number, right? You can always put 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. Right? You can't list them all. So that's how you know if it's discrete or continuous, if you can list it. So you list the events, and then you list the probabilities. All right. For a probability distribution to be valid, the probabilities of pi, so each individual one, must be between 0 and 1. That was just like last chapter. And when you add up all the probabilities, they all add up to be 1. All right. So when you add up all the events, you get a probability of 1. So we can analyze distributions of quantitative data in Chapter 1. We made it a point to discuss their shape, center, and variability. That was part of our SOVC plus context. So we'll do the same distribution for random variables. So you have a histogram with the probabilities on the left on the y-axis and the APGAR score on the x. So each one are the possible outcomes, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And those are your possible outcomes. So the distribution is skewed left, right? Very few data points here and a big chunk to the right. So it's always skewed in the direction of the tail. So skewed left with a single peak at an APGAR score of 9. See how they get in that context too? They tell you what the APGAR score is. And that single peak is at 9. The probability distribution of the random variable x models the population distribution of the quantitative variable APGAR score of a newborn baby. So we can interpret our earlier result. So the probability that x is greater than 7 would be, if I'm greater than 7, that would be like adding, hey, that would be probability like 8, 9, and 10. So I would add those probabilities together. Probability of 8 is just over 0.3. Probability of 9 is probably like 0.45. Probability of 10 is probably, again, maybe 0.5. So together, this is going to be right around 0.8. All right. It's hard to see because we don't have the exact numbers, but you can still pull the information from the histogram, knowing the probabilities are on the y-axis. All right. So let's do a problem. Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to 6 passengers. Pete charges $150 per passenger. Let C equal the total number of amount of money that Pete collects on a randomly selected trip. The probability distribution of C is given in the table. So this is why C is really important. It's super important that you clearly label what your variable is. C equals the total number of money that Pete collects. So the number of passengers could have been a different variable, right? That would be, you have to have at least 2. So that would be 2, 3, 4, 5, or 6. But that's not what we're counting. We're counting the amount of money collected. It's 150 per person. So the least amount of money they would select is 2 passengers. So that'd be $300. Then 3 passengers would be 450, 6, 750, and 9. So I'm looking at the total amount of the total amount of money I collect, and then their respective probabilities are below. So to make my histogram, I put my x variable, right, my random variable on the x-axis. So it'd be 300, 450, 6, 750, 900. And then my y-axis is the probability of each one. And then I just make my little bar. So 300 is the lowest one. I'm just above, I'm at 0.15. And then 0.25, 0.35, 0.2, 0.05. All right. And now we can talk about the graph is roughly symmetric, all right, with a single peak at $600. So that single peak here is going to tell us what the most common or most likely, the most common occurrence. So it happens the most often is $600. So that's we just talked about the shape, right? And then we talked about center and spread. So the way we talk about center here, we're actually going to talk about the mean, okay? So the mean, another name for mean is called the expected value. All right, so if you see those two in this chapter, they are synonymous. So the mean or the expected value of a discrete random variable. So the mean, and that's the subsection. So the mean expected value of any discrete random variable is an average of the possible outcomes, but a weighted average in which outcome occurs is weighted by its probability. So the more likely an event occurred, the kind of more it's weighted towards it. So to find the mean or the expected value, there's a lot of words here. It's not too bad. I'm going to read it to you, and then I'll give you the shorthand version. The mean or expected value of a discrete random variable is its average value over many, many repetitions of the same process, chance process. That's the same idea as our law of large numbers, right? The probability of something occurring is not exactly that, but the definition of a probability of something occurring is after many, many, many trials. Same idea here, all right? So suppose that x is a discrete random variable with probability distribution. So you get x1, x2, x3, these are the events, these are the probabilities. To find the mean or the expected value of x, you multiply each possible value of x by its probability and you add them together. So you take the event 1 times by its probability, plus the second event times by the probability, plus the third event times by the third probability, and so forth. And you do that until you get all of them. Whatever that equals is your mean. All right. Some notation. Mu of x, right? Mu means mean. The sub x tells you, hey, this is the mean of the random variable x. That is also equal to capital E means expected value of x. All right, and there's the formula. Here is the shorthand. It is the sum of all those. So on the AP test, what is common practice in math is to show the first term plus the second term plus dot 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 plus the last term. So if there's like 6 events here, I would do the first one plus the second plus dot 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 plus the sixth one. Then I would write it out as this, multiply them together in the same form, and then I'd add them together, and that'd be my answer. That's how I'd show proper notation. We'll practice this a little bit in class and so forth, but that is the correct notation. So just a recall, the median is the middle value, the mean is the balance point. All right, so it's where it's evenly weighed on both sides. All right, it keeps this balanced. So how do we interpret the mean? This is just telling us, hey, so the mean of some distribution is $562.50. So this is based on that safari trip. If we randomly select many Jeep tours, Pete will make about $562.50 per trip on average. That's how you interpret it. If we randomly select many X or whatever's going on, Pete will make about blank on average. Right? This being our mean or our expected value. All right. Here is another one for expected value. So earlier we defined the random variable x to be the Apgar score of a randomly selected newborn baby. The table gives the probability distribution of x once again. So here are my potential events. This is what that histogram looked like from. So on the Apgar score, I could score anywhere from 0 to 10. It is discrete, so 0, 1, 2, and so forth. And the probabilities are below. Calculate and interpret the expected value of x. So I'm going to do 0 times this, plus 1 times this, plus 2 times this, plus 3 times this, plus 4 times this, plus 5 times this, plus 6 times this, plus 7 times that, and so forth, all the way up to 10. So, like I said, I show the first one 0 times 0.001, plus 1 times 0.006, plus dot dot dot, plus the last one 10 times 0.05. I add them all together, I get 8.128. All right, and then to interpret it, in many newborns are randomly selected, their average APGAR score will be about 8.128. Don't forget the about, even though you say many, all right, that allows you to do that like law of large numbers idea, but the about is because it's not guaranteed, right? It's about, it's estimated, but it's a very good one. So how can we find the median of a discrete random variable? We can find the median for a cumulative probability distribution. The median of a discrete random variable is the 50th percentile of the probability distribution, right? Same as before, 50% above, 50% below. So if I'm looking here, I'm going to look at the cumulative relative frequency. So if I'm at 0.15 and then this is individually 0.25, the cumulative probability, remember, that is when I add all of them up below. So the cumulative probability always adds to 1. That's one way to tell to make sure that, hey, this is a valid probability model. If you do the cumulative relative frequencies, or cumulative probabilities, I mean, they should add to be 1, is your last one should be 1. All right, so here I could look at the cumulative and I see I'm between 0.4 and 0.75. So between 4.5 and 600, between 450 and 600 is a 50th percentile. So The question is which one? If it is a discrete random variable, the smallest value for which the cumulative probability equals or exceeds 0.5. So since I don't hit 0.5 at 450, I don't want to include that because I'm too low. So I have to at least hit 0.5. So that's going to be $600 here. Now talking about variability, that the V in SOVC. So the standard deviation and variance, which is the word we've talked about, but not a ton, of a discrete random variable. So with the mean as our measure of center for a discrete random variable, it shouldn't be a surprise that we'll use standard deviation as our measure of variability, right? Mean and standard deviation go together, median and range usually go together. So we should be using standard deviation here. And again, this formula looks very messy, but it's not too bad, okay? The standard deviation of a discrete random variable measures how much the values of a variable typically vary from the mean, all right? So suppose you have the random variable process again, x1, x2, x3, p1, p2, and p3. So we find the mean, and we'll just call it x, all right? That mean is mu x, all right? It's some number. The variance, remember, variance is the standard deviation squared, the only difference. So oftentimes, even in chapter 1 and 2 and stuff, you found the variance and then you just took the square root to get your standard deviation. But it's just another way to calculate it. So variance, right? That is take the x value minus the mean, we square it, and times by the probability. So before, right, when you found the regular standard deviation, you took the value minus the mean and squared it, plus the value minus the mean, square it, plus the value minus the mean, square it, all divided by n, or divided by n minus 1. So instead of dividing by n minus 1, you multiply each event by its probability. So x minus mean squared times probability, plus x minus mean squared times probability, plus x minus mean squared times probability, and so forth. All right. To find the standard deviation, all you do is you take the square root of it. Take the square root of the variance. All right. And that's the same formula or same outlook as the regular one, as regular standard deviation. Again, good practice will be the first event plus the second plus dot 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 plus the last one. So calculate and interpret the standard deviation for our APGAR score. So we had already known that our mean was 8.128. So now we do 0 minus that squared times probability. Plus, they really should do the second one, plus 1 minus 0.8128 squared times probability plus dot 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 plus the last one. This got messed up. All right, pause here for a second, people. Might as well add it in at this point since it's wrong. And so you'll see, look. .06. And then there should be 10. We're going to keep going with it. So this is what it should look like. All right, first plus the second plus dot 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 plus the last. I'm gonna assume that this number was calculated correctly. To be honest, the number doesn't really matter for right now, as long as you understand the process of it. All right. So it's 2.066, but remember that's the variance. To find the standard deviation, you have to take the square root of it. You get 1.437. All right. Then to interpret a randomly selected newborn baby's APGAR score will typically vary from the mean, which is 8.128, by about 1.437 units. Same kind of interpretation as before. It's the typical distance you vary from the mean. Here, it's just, yeah, it's the same idea. Right. So that's all for discrete random variables. All right. For continuous random variables, all right, a continuous random variable can take any value in an interval or on the number line. Discrete, you are taking jumps. Continuous, you find any value. So the probability of an event occurring, a continuous random variable, is the area under the density curve and directly above the values on the horizontal axis that make up the event. We've seen this in chapter 2 without really realizing what we were doing. So say I have a density curve. All right, it's at 1/9. All right, remember the area underneath the density curve is always 1. So if I added from 0 to 9, right, found the area, it should be 1, which is exactly how I got this height, right? If this length of this rectangle is 9, then the height has to be 1/9 because the area underneath the curve for a rectangle is length times height. Well, 9 times 1/9 is going to equal 1. So that's how I know this height is 1/9. If I want to find the probability that I am between 3 and 7, 3 and 7, that's 1, 2, 3, 4. I have a width of 4, a height of 1/9. So it's just 4/9. Okay. Remember that for continuous random variables, it's always a range. You cannot find an individual value. All right, like if I want to find, hey, what's the probability that y equals 3? Well, my width, right? What's my width? It's 0 because it's just a line. There's no width here. And my height is 1/9. So 0 times 1/9 is 0. The probability of an individual event happening in a continuous random variable is 0. You always, always, always have to find it for a range. That's why it's from 0 to 6 or 0 to 7. An interval is probably a better word. Always have to find it for an interval, 3 to 7 in this case, or bigger than 5, or smaller than 2. Always has to be an interval. All right. So here's a problem. Selena works at a bookstore in the Denver International Airport. She takes the airport train from the main terminal to get to work each day. The airport just opened a new walkway that would allow Selena to get from the main terminal to the bookstore in 4 minutes. She wonders if it would be faster to walk or take the train to work. Let y equal Selena's journey's time to work in minutes by train on a randomly selected day. The probability distribution of y can be modeled by a uniform density curve on the interval from 2 to 5 minutes. Find the probability that it will be quicker for Selena to take the train to work than to walk that day. So interval from 2 to 5. So I'm going to go 2 to 5. All right. To find the height of my density curve, again, that's always the width of my interval, which is 3, right? 1, 2, 3. And I know the area under my curve has to be 1. So the area equals 1. The way to find the area of a rectangle, if it's uniform distribution, it's always a rectangle. All right. So the height is width times height. My width is 3. 3 times height equals 1. My height is 1/3. That's how I find the height of a density curve. Okay. Now the question is, find the probability that it will be quicker for Selena to take the train than to walk that day. Well, it says it's going to walk is 4 minutes. So in order to be quicker, I have to be less than 4 minutes. I'm going to find probability that I'm less than 4. Well, that would be a width now of 2 times the height, which is 1/3, so 2/3, or 0.667. This is a good statement right here. Probability that y is less than 4. Remember, y is the time it takes in minutes by train on a randomly selected day. Probability that y is less than 4 is 2/3, or 0.667. So to interpret, there's a 66.7% chance that it will be quicker for Selena to take the train to work on a randomly selected day than walking, you could say. All right. So that's one continuous variable. The other continuous variable we'll look at in this class is the normal distribution. All right. So the heights of young women can be modeled by the normal distribution with a mean of 64 inches and a standard deviation of 2.7 inches. Suppose we choose a young woman at random and let y be her height in inches. Find the probability that she's between 68 inches and 70 inches. Interpret this value. So the probability then between 68 and 70. And again, my x-axis is my variable. Y is women's height. So you could find your z-scores, right? Remember that is x minus mean divided by standard deviation. So 68 minus 64 divided by 2.7. You find your two z-scores. And using table A, you can go ahead and find that. You would have to find the probability rate. Table A is always from the left to the right. So it would be all this shaded region minus all this shaded region would give me this left over. This is how you do it, table A. Or you could use your technology, and I'll show you right here on the calculator how to use the technology. this happen? That's not what I want to do. There we go. Okay. So I'm gonna turn it on. Remember, I'm gonna go stat. There's not. Sorry, I'm gonna go second vars. And I'm gonna do normal CDF. All right, because I'm finding the probabilities. Normal CDF is finding the probabilities. Inverse norm helps me find the bounds. I know my bounds. I'm gonna go to normal CDF to find the probability. My lower bound is going to be. I'm gonna do both. I'll do the z-scores first. My normal bound is gonna be negative or 1.48, comma 2.22. I don't have to, but my mean is 0, standard deviation is 1. Since I normalized it, you don't have to put those in. The calculator assumes it's 0 and 1 unless otherwise told. Press enter, get 0.056. Right. If I want to just do it with the values, normal CDF, this will be 68, comma 70, comma my mean, which is 64, comma standard deviation, which is 2.7. Enter, boom, get the same thing out. Remember, if you do choose to use technology instead of table A, you have to write this out. Lower bound is 1.84, upper bound 2.22, mean is 0, standard deviation is 1. Have to write it out in order to get full credit. Or you could write normal CDF, lower bound 1.68, comma upper bound 70, comma mean 64, comma standard deviation 1. All right. So that is my value. Remember, continuous random variable, I had to find it of an interval from 68 to 70. I could have done larger than 70 or smaller than 59 or whatnot, but it has to be an interval. All right. So then to interpret it, the probability that a randomly selected young woman has a height between 68 and 70 inches is about 0.056. All right. And those are our learning targets today. So thank you for watching 6.1.